Hello everyone. We will be solving a problem on position vectors and Cartesian 3D vectors. Typically, given the position, we need to find the components and so on, or the projections and so on. Okay, so here is the problem. Okay, so problem. Okay, there are two cables running from point A to points B and C as shown. Okay, the figure is going to be drawn in a minute. Okay, and the important thing to understand is in statics, cables are always in a state of tension. Okay, so cables are always in a state of tension, which means that there is a force acting along the line of the cables. The cables in the direction shown in the figure. Okay, so that's something that I want to make a note of. Cables are always in a state of tension, at least in statics. Okay, if they take slack, then there is no force on that particular cable. So here is the situation that I'm going to be drawing. Okay, with that particular premise, I'm going to draw the x, y, and z coordinate direction. So this is the z-axis, let's say. Then this is the x-axis here, which I'm drawing, and then in a minute I'm drawing the y direction. Okay, so this is the origin of the coordinate frame. This is the x-axis positive y direction, and positive z direction. Okay, I have the point A, which is situated on the y-axis. So starting from point A all the way to some point here, okay, that I'm going to call as point B. Okay, then I have another cable which is running from point A to point C, as I'm going to be drawing in a minute. So from point A all the way to some point here, that's another cable, point C here. Okay, so this is A. And you are told that along the cable AB and AC, there are forces because the cables are in a state of tension. So I'm going to draw those forces here. So there is a force whose line of action is from point A to point B. Okay, so this is the force FAB. This is a force whose line of action is directed from point A to point B. Okay, so that's one force, and then I have another force which I'm going to mark on this figure here. So there is the force FAC. Okay, so this is the force FAC, and FAC, you know, if you look at that force, I guess I want to write it separately out there. So FAC is a force whose line of action is directed from A to C. Okay, the key word being line of action, and you have already seen that line of action is nothing but the direction along which the force is acting. Okay, so the line of action of the force, and this is the direction of the arrow that is pointing in the figure. Okay, besides this information, I'm also given some information regarding the position of points A and B. Point A is situated at a particular distance from the origin, which I'm going to draw in a minute. Okay, so this is the distance of point A from the origin O. Okay, and this is 3 meters. And then I have the point B and the point C likewise along the x direction. This is at a distance of 1.5 meters. Point C is at the same distance as point B along the x direction. Okay, that's also 1.5 meters. Okay, just to prevent confusion, I'm going to remove this thing there. Okay, and then I can extend the height of that guy. Okay, so that's the z-axis for me. And then the height of point C, parallel to the z-axis, right, is going to be the height of point C, and this is given to me as 3 meters. And likewise, the height of point B is also given to us. Okay, this height is given to me as 1 meter. Okay, and then I'm going to draw them as dotted lines because these are all dimensions. Okay, so typically when you look at my problems, you'll see that if I show something with dotted lines, then that implies dimensionality. Okay, and likewise I have something here as well. All right, what are the things I'm supposed to find in this particular problem? Here is what I need to find. Okay, so find the resultant of the forces FAB and FAC. Okay, that's about it. Sorry, this is not a straight line. Sometimes I can't draw straight lines for the life of me. All right, here is what we're going to be doing now. Okay, so our key idea is that the resultant force is nothing but the vector sum of these two forces, FAB and FAC, and you're given in the problem the magnitudes of these two forces. So the magnitude, so you're also given, before I get ahead of myself, magnitude of FAB is 560 newtons, and the magnitude of FAC is 450 newtons. All right, okay, so this is information that is given to us. Okay, so this is given, and then what do we need to find? Okay, find the magnitude and direction of the resultant of these two. Okay, and the key idea that we are using here once again is that the resultant force is the vector sum of the individual forces. Okay, there is no surprise in that. This is fairly straightforward. Okay, here is typically the trick that I employ. Okay, whenever I come across problems of this nature, the first step is this: whenever we come across problems whose dimensions are given, then write down the coordinate of the points of interest. Okay, what are our points of interest for us? Right, what are our points of interest? I have the point A, the point B, and the point C. That's about it. Okay, points of interest are A, B, and then C. Okay, because the forces are directed from point A to point B, A and B are points of interest. Forces are directed from A to C, C and A are also the points of interest. I have already accounted for A, so I'm just going to do points B and C. What are the coordinates of these points? Point A is fairly straightforward, right? It's a point on the y-axis, so it will not have anything along the x and the z, only coordinate along the positive y direction. Okay, so I can write the coordinate. Okay, so for point A, the coordinates will be 0, 3, and 0 so many meters. Okay, this is the units or meters. Okay, then what are the coordinates of the point B? Look at the point B. It's 1.5 meters along the negative x. It's sitting on the origin with respect to the y-axis, and it's raised by a height of 1 meter. Okay, so look at the figure and then go back and then write down the coordinate of point B to be minus 1.5, 0, and then 1, so many meters. And then lastly, the coordinate of point C. Point C is like the exact opposite of point B, except that it's raised a little higher than the point B. So 1.5 along x-axis, 0 along y, and 3 meters along the z direction. Okay, so the coordinates of point C are 1.5, 0, and then 3 meters. Okay, this is an important step in this particular problem, and you'll see why. Okay, then the next key idea that we're going to use is this. I'm going to call this as key idea 2 because we already had a key idea here. So I'm going to call this as key idea 1. Okay, this is a fairly obvious one. The next key idea 2 is the following. Break the force into their components, which you know. Okay, break FAB and FAC into components. Of course, it would be nice if the coordinate direction angles were given, right? But they are not given. If the coordinates of the points are given, then use the idea of position vectors and unit vectors. Okay, and since coordinates of A, B, and C are given, we can use the idea of position vectors and unit vectors. Okay, so that is the key point that you're seeing here. And so we go back to our roots and we say, okay, I'm going to take the force FAB. Okay, if I take the force FAB, then here is what I can say. Okay, this force, by making use of the fundamental rule, the force FAB is its magnitude times the unit vector. Okay, so UAB is the unit vector along line of action of FAB. Why is this UAB and not UBA? And not UBA? This is because the force FAB is directed from A to B and not, so A to B and not from B to A. Okay, where do you see this? This is typically seen when you come to the figure. You see the forces from point A to point B, right? It is not from point B to point A. Okay, so which means that the unit vector UAB is along that particular line. So I'm just going to draw it in a different color. I'm running out of colors here, but I guess I could probably use maybe this kind of a different blue. Okay, so this is the unit vector UAB. I'm just marking that here. So this is UAB. And likewise, I can also mark the unit vectors UAC because the force is from A to C. I'm going to have a unit vector which is directed along that particular line, which I'm going to call as UAC. Okay, these are all U's. The tail of my U is fairly long, as you can see. Okay, so that's a U. Okay, and that's UAB. All right. Now, one thing that we can do is the following. So I'm just sitting on force FAB yet, right? So which means that FAB is FAB UAB. But what is a unit vector? Unit vector is position vector by its magnitude. So this is going to be FAB times RAB divided by the magnitude of RAB, where we have used the fact that UAB is RAB by its magnitude. Okay, how do you find the position vector? This, if you go back to our lectures, you will find out that position vector from point A to point B is the coordinates of B minus the coordinates of A. Minus the coordinates of A along the respective directions, okay, accompanied by their respective unit vectors. So which means that if I'm going to write R A B, and if you want, for reference, you can bring in the coordinates A B because they are of interest to us. I can copy this and then I can bring that creature and then paste it right here, right? So if I have these two sitting right next to me, and I'm gonna scrunch that out, I'm sorry, so that I have a little more space. Okay, so this is in meters, so I'm essentially using this information, okay, to find the position vector. So this is going to be the following, okay, so B minus A, so minus 1.5 minus 0, so that's minus 1.5 I. Then I'm going to have 0 minus 3 J, and then I'm going to have 1 minus 0 K, okay, which tells me that RAB is minus 1.5 I minus 3J plus 1K, so many meters. Okay, that is very important that we have the units done, which tells me that the magnitude of RAB is the square root of the sum of the squares. When you square numbers up, whether they are negative or positive, they all become positive anyways. So square root of that will give me the magnitude, which is approximately 3.5 meters. Okay, which tells me that UAB is RAB by its magnitude, and so this is going to be minus 1.5 I minus 3J plus 1K, all of it divided by the magnitude, which is 3.5. Unit vectors are dimensionless, but they have a particular direction, okay. Alright, so with this information, I'm now ready to write the force FAB. So FAB is the magnitude times the unit vector, and magnitude of FAB was known to us, right? This was approximately 560 newtons, so this is 560 times minus 1.5 I 3J 1K, all of it divided by 3.5. Just for this particular case, let me do it piece by piece. Okay, so this is going to be FAB is equal to 560 times minus 1.5 divided by 3.5 I plus 560 times minus 3 divided by 3.5 J plus 560 times 1 divided by, divided by 3.5 K, and so if you crunch the numbers, you end up getting FAB as the following. Okay, so I'm going to go look at my numerical work where I have calculated FAB. So this is minus 240I, and then I'm going to have minus 480J, and then I'm going to have 160K, so many newtons. Okay, we're almost there. Once again, straight lines are becoming my bugbear. Alright, then I go to the next force. Okay, so the next force is FAC. Okay, how do I handle FAC? How did I handle FAB? I go back to FAB and I say, okay, FAB is magnitude times its unit vector, so same idea for FAC as well. So I'm just going to call this as A. Okay, so FAC, if I follow the same color scheme. So this is FAC. So FAC magnitude times the unit vector AC, which we had already marked on the figure that you see here. Important thing being that, okay, why is it from A to C? That's because that's the direction of that force. If it were pointing from C to A, then the unit vector would be UCA. Okay, there is nothing special about it. And so by basic understanding of what a unit vector is, this is the position vector divided by its magnitude. How to find the position vector? I take the coordinates of A and C and subtract them from each other. So this is the coordinates of C minus the coordinates of A. Okay, and we already have the coordinates of A and C and B written up here. Okay, so I'm just going to borrow that and maybe bring it down there. I don't need B in reality. Okay, so if I bring in the coordinates of A and then get rid of B, bring my good friend C up here and then write this in meters as well. So using this, I can find out that RAC is the following. It's coordinates of C minus A, so 1.5 minus 0 in the I, and then 0 minus 3 in the J, and then 3 minus 0 in the K. Or if I simplify it, RAC is 1.5I minus 3J plus 3K, so many meters, which means that the magnitude of RAC is 1.5 square, 3 square, 3 square, whole to the power 1 by 2. And if you crunch the numbers, this is going to give you 4.5 meters. Okay, so once I have these, then I can say that, okay, FAC, which is magnitude times unit vector, magnitude times position vector by its magnitude. And so this was AC had a magnitude of 450 newtons. Okay, so this was 450 times 1.5I, 3J, 3K, all of it divided by 4.5, right? And if I crunch the numbers, I'm not going to do this because we already did it for the previous one slowly, step by step. FAC is going to end up being the following. Okay, so FAC is 150I. Then I'm going to have minus 300J. And then lastly, I'm going to have plus 300K. So many newtons. Okay, and I want to underline this particular answer as well. Alright, so we found out FAC, we already had FAB here, so FR is nothing but the vector sum of these two. I'm going to skip some steps. Is the vector sum of FAB plus FAC. Okay, so this is going to end up being the following. So FAC 150I, this was minus 240, so minus 240 plus 150 in the I. Then I'm going to have minus 480J minus 300, I'm sorry, minus 480 minus 300. I don't need to write the J inside here. And then this one, if I can sneak this in here, that is 160 plus 300K. Okay, which means that my resultant is going to be the following. Okay, so FR is going to be minus 90I, then minus 780J, and then plus 460K. So many newtons. Okay, so this is the resultant vector which we have found out. Okay, then I can find its magnitude is 90 square, 780 square, 460 square to the power 1 by 2, and this is going to give me approximately 916 newtons. Okay, so this is the magnitude. This is the Cartesian form which I have written here. This is the Cartesian form of FR. This is the magnitude of FR. Okay, if I have to find its coordinate direction angles, what do? You would have followed my previous example and then you would compare with the standard form. Okay, if you compare the numerical answer with the standard form, which is FR cos alpha R I, FR cos beta R J, FR cos gamma R K, right? So you compare these two creatures, which I'm going to mark with an arrow. Okay, so you compare this and that, and then you will immediately realize that, okay, hey, FR cosine alpha R is equal to minus 90, which means that alpha R can be found out. Okay, alpha R, after I do the math, is going to be the following. So this is cos inverse of minus 90 by 916, and this is going to give me an obtuse angle. Okay, so this is around 96 degrees. FR cos beta R is minus 780, so beta R is cos inverse minus 780 by 916, one more obtuse angle, so 149 degrees approximately, and then FR cosine of gamma R is equal to 460, so gamma R is cos inverse 460 by 916, or this is approximately 60 degrees. Okay, and it can be seen that if I write the magnitude of FR in the x, y, and z directions, okay, so this tells me that if I write FR as FRXI, FRYJ, FRZK, FRX will be negative, which means that along the negative x-axis. Okay, FRY will be negative 2, which means along the negative y-axis, and then likewise FRZ is going to be positive. I'm sorry, I was in a negative mindset. Okay, which means along the positive z-axis. Okay, I guess I don't need that. All right, now all I wanted to do was put a nice bracket around these things, but other things start happening which we don't have much of a control over. All right, now all I want to do lastly is draw these forces in the Cartesian plane. Okay, so just by comparison, you can see that obviously here is the final result that we have. Okay, so final result. Okay, here is what I have. FR, which is the vector sum of FAB and FAC, will give me the following value. So minus 90I, minus 780J, okay, and then 460K, so many newtons. Okay, and then I have alpha R is equal to 96 degrees, beta R approximately 149 degrees. Okay, and then gamma R is approximately 60 degrees. Okay, and then the magnitude of FR in the x direction is 90 along negative x. FRY is 780 newtons along the negative y, and FRZ is 460 newtons along the positive z. Okay, so these are our final answers, and one with very last figure, I will complete this particular problem. How to draw this now? Alright, first draw the Cartesian coordinate frame. Okay, so draw the x direction, y direction, and the z direction. So this is the x direction, y direction, and the z. Alright, and the y direction here. Okay, here is the origin. So this is positive x, which means that the unit vector along this direction is going to be minus I. This is positive y, which means the unit vector along this direction is going to be minus j, and this is positive z, so the unit vector here is plus k. Then I see, okay, hey, look at frx. Frx is along the negative x direction, so first draw that guy. Okay, so that's going to be along the negative x direction right here. Okay, I'm going to call that as frx. Then I'm going to draw fry, which is also along the negative y. Okay, so that's a slightly larger magnitude, so I'm just going to draw that guy right here. Okay, so starting from the same origin, this is going to be fry. Then I can complete the parallel pipette, if you want to call it that way. Okay, so I'm just going to copy that and paste that here. Okay, then copy this and then paste that there, if you will. Okay, so here is the situation, and then the other thing I'm going to do is I'm going to draw frz, which is along the positive z direction, as you can see from the figure here. So this is going to be frz. Then complete the parallel pipette. Okay, copy and paste right here. I'm going to do a couple more of these, one here and then one more right there. And then I'm going to take that creature, complete that. I'm going to take that creature and then complete that. Okay, just for the sake of my convenience, I'm going to get rid of this guy. Okay, we know that this is along the z direction. Then I need one more of these. Okay, and one very last thing. Now my parallel pipette is complete, which means that my resultant force vector is going to be in the following direction. Okay, so my resultant force, which I'm going to draw in this color, is going to be directed starting from here all the way to the outermost corner of this parallel pipette, as you can see here. Okay, so this is going to be the resultant force Fr. And a couple of things that you want to note down is, okay, this angle that you see here is going to be gamma r. Okay, then you will see that another angle that I can mark is beta r, all the way from here on to the positive y direction. That's going to be beta r. And then one more angle that I can kind of mark here is the angle made with respect to the x-axis. Okay, so this is with respect to that axis, this with respect to the z-axis, and then this is going to be alpha r. Okay, and this is typically how you draw the resultant vectors. All right, fantastic problem. I hope you had fun as much as I did in doing this problem. Thank you very much, and I'll see you all in a new set of video lectures next week. All right, take care of yourselves.